Let's try to solve this question over here. A support cable on the bridge has an area of cross-section 0.0085 meter square and a length of 35 meter. So this is a cable that you can find on the bridge. Usually bridge, right, sometimes they have suspension on top to hold the bridge, to prevent it from curving downwards. Okay, so that kind of support cable, we have that kind of support cable over here. Then they say that this cable here has an area of cross section 0.0085 meter square. So cross section area is this one over here. So the area here is mentioned to be 0.0085 meter square. Then this length of this support cable here is equals to 35 meter. It is made of high tensile steel, so this is a kind of steel that we use to make this cable over here. And this steel over here, this material here, the Young's modulus for this material is 2.8 times 10 to the power of 11 Pascal. So that's the Young's modulus of this particular material. Okay, so the tension in the cable is 720 kilonewtons. So you are going to stretch this support cable, or you can say this cable here, because it's suspending the bridge, right? So there's some tension experienced by the cable, and this tension over here has a magnitude of 720 kilonewton. So this is kilonewton, have to be very careful. Don't forget the kilo over here. 720 kilo times 10 to the power 3 Newton. Okay, so that's the force experienced by this support cable over here. So now let's try to look at the question. The question asks for the extension of the cable. So how much does this cable being stretched? What's the change of length experienced by this cable over here? Then the next thing is the strain energy stored in the cable. So strain energy later we'll go through it, but first let's go through the extension. Well, this is a very straightforward chapter actually. Deformation of solid. When you have Young's modulus, you see the force, you see the A. The force and the cross-section area here will allows you to determine the stress. The length over here together with the change of length will form the strain, and stress divided by strain you get your Young's modulus. So we are going to apply the same strategy over here. So know that Young's modulus is stress divided by strain, which if you expand, it will be force divided by area divided by the change of length divided by the original length. So you have most of the values, so let's just substitute it. The Young's modulus is 2.8 times 10 to the power 11. Then your force experience is 720 kilonewton divided by the cross-sectional area, which is 0.0085. Then you have your change in length, which is unknown, which is what you want to find, the extension, which is the change of length. Then you have your original length, which is 35 meter. Okay, so if you put it in everything into your calculator and you determine the change of length experienced by this support cable over here will be 0.0106 meter. Okay, so this is the change of length experienced by the cable, or you can call it as the elongation experienced by the cable, or the extension experienced by the cable. Okay, next you have your strain energy stored in the cable. Well, strain energy, right, in our syllabus, if you are asked to determine strain energy, there's some assumption that we need to make. Okay, we are only able to determine the strain energy if the amount of stress that is experienced, or the amount of strain that is experienced, does not exceed the proportionality limit. Okay, we will need to assume the stress and strain to be below the proportionality limit. Only we are able to calculate it, because let's slightly explain it. Okay, so the stress strain graph, let's slightly sketch it. A stress strain graph looks something like this. You have your stress, you have your strain here, then the graph will start with a proportional area, then it starts to get non-linear, then it starts to rise, and after that it falls. Okay, the strain energy, yes, the strain energy is actually the area under this graph over here. This whole part over here is the strain energy. Okay, but if you want to determine this strain energy and over here, it's not doable at our level. Okay, our level, we are not able to calculate it because this requires some advanced integration technique because it's an irregular shape. Okay, it's an irregular shape. To determine its area under the graph, you need integration, which is not in your syllabus. You haven't reached it yet for your mathematics syllabus. So for now, we could consider it not doable at our level. Okay, but if you restrict yourself to the stress and strain which is below the proportionality limit, let's call this a proportionality limit, means by your stretch or your stress and your strain, if it's below this proportionality limit, if it does not exceed this limit, right, then if you see here, this area over here can be easily calculated because this strain energy is just, oh, this is not strain energy. I am so sorry. This is not strain energy. This is strain energy per unit volume. I have to change this graph here to become force against extension. Okay, then this will be strain energy. Very sorry, very sorry. Okay, so this strain energy here can be easily determined. And because it's a simple triangle, you know that triangle to determine its area is actually quite straightforward. So now you can determine the strain energy to be half times the height, which is the force experienced by force times the width of the triangle, which is the extension. So this is just the equation for strain energy. Okay, it's much more simpler if you keep your stress and your strain to be below the proportionality limit or within the proportionality limit. Once you exceed it, right, then it becomes non-linear already. Then to determine the area, you have to use integration to determine the area, which is out of our syllabus currently. Okay, so that's why for any kind of situation, if we are asked to determine the strain energy, we have to make the assumption that it's below the proportionality limit. Okay, so if you make the assumption already, now determining the strain energy is just using the equation I mentioned, which is half multiplied by the force multiplied by the extension or the change in length. So the force experienced here is 720 kilonewton. Then the change in length, as what we determined earlier, is 0.0106. So if you perform your calculation, you get your answer for your strain energy to be 3.8 times 10 to the power of 3 joule. So this is the strain energy that is stored inside this cable when you stretch it by this force and extended by this amount. Okay, if you experience this force being used to pull it, and the extension that is experienced is this amount of extension, then you know that the amount of strain energy stored in the wire will be by this amount. Okay, that's the idea over here. Okay, so it's a very direct question. Basically, you just manipulate your Young's modulus equation in order to solve this problem, and to know that if you want to determine strain energy, you have to keep it within the proportionality limit in order to do so. So that's it for this question. Thank you very much.